How's it going, everyone? In today's video, we're going to look at how Pytest simplifies test code compared to Python's built-in unit test module. Unit test works fine, but it comes with a fair bit of boilerplate, such as subclassing, using test case, writing setup methods, and using special assertion methods like assert equal everywhere. In this first file, we'll test a simple calculator using Unittest, so you can see what that boilerplate looks like. Then, in the next file, we'll rewrite the same tests with Pytest, and the difference will speak for itself. Now, before we begin, I'd just like to thank Zed for sponsoring this video. Zed is a lightning-fast code editor written in Rust, and I've been using it to do all my coding for a while now. If you feel like trying out Zed, I've left a link in the description box down below where you can download it for free. Anyway, let's get started. So the very first thing we're going to want to do is import Unittest, which is Python's built-in testing framework that comes with the standard library. Then we're going to create a calculator class. And this will be a simple calculator class that we'll write tests for. First, we'll create a docstring that describes what the calculator does. As you can see here, it's a basic calculator that stores a running total and supports add, subtract, multiply, and divide operations. Then we will define our init block. This will be a constructor with an optional starting value, and the default will be set to 0. Then we will store the initial value in a private attribute, so we can track the running total. Below that, we will create a property, so we can access this value as an attribute. Next, we'll define some methods we can use with the calculator class, such as the add method, which adds the given amount to our running total. And here we want to increase the value by the amount specified. And we're going to do the same thing for subtract and multiply. But for divide, we're going to make sure that we take care of what happens when the user tries to divide by 0. So if the amount is equal to 0, we will raise a value error stating that we cannot divide by 0. Otherwise, we will divide by the amount specified. And at the bottom, we will have a reset method, which allows us to reset the running total back to 0. Now let's write the tests using Unittest. The key things you'll notice are a class inheriting from test case, a setup method that runs before every test, and special assertion methods. With Unittest, you can't just use plain assert and get useful output, so you reach for assert equal and friends. So let's create this Unittest test class. And our test class must inherit from unittest.testCase to work with the framework. And again, we're going to define a docstring that describes what this class does. Here it states that it tests for the calculator class using Python's built-in Unittest module. Below that, we define a setup method. And this runs before every single test method to give us a fresh starting state. And here we're going to create a brand new calculator instance, so each test starts with a clean slate. And again, this will run before every single test method. Then we can define some basic arithmetic tests, such as test add, and here we have a docstring that describes the expected behavior of this test, followed by the actual operations. So here we add 5 and 3, and then we assert equal that the expected value should be 8. Then we do the same thing for subtract, for multiply, for divide, and also for the error we can encounter when trying to divide. Note how descriptive the function name is here. Test divide by 0 raises error. It states exactly what should happen. Try to keep this as concise as possible. But it's also okay if these names become quite long. Inside, we use Unittest's assert raises context manager to check for the exception. And then we provide the code which should raise a value error, because you can't divide by 0. Then below, we also check that the error message is correct. And to do that, we capture the exception context so we can inspect the error message. Then once again, we trigger the division by 0 error just like in the previous test. And finally, we can assert equal to make sure everything's working as expected. Then we have integration style tests, which in other words means chaining operations. As you can see here, we're chaining add, multiply, subtract, and divide. Then we are verifying that chaining all 4 operations gives us the expected value. And finally below, we have some state management tests. The first one tests that a freshly created calculator starts with a value of 0. And all we're doing inside here is using assert equal to check the value and see whether it's set to 0. Then we have a test which tests that the reset method correctly puts the value back to 0. Here we'll first add 100 and then call reset. And once again, check that the value is set to 0. And finally, we have a test which tests that we can create a calculator with a non-zero starting value. So here we create the calculator with an initial value set to 42. And then we check that the value is set to 42. Now the last thing we're going to do is create our if name is equal to main check and our main entry point and call unittest.main. Now when we run this, it will state that it ran 10 tests in 0 seconds. And since there were no problems here, we got OK as an output, which means all the tests passed. But look at everything we had to write. A test case subclass, a setup method, self.assert equal on every line. This entire class was what it took to test the calculator. It's a lot of framework scaffolding for 10 straightforward checks. In the next file, we will rewrite the same tests with Pytest, which, as you'll see shortly, will be much easier than what we did here. Now, before we start using Pytest, it's important that you install Pytest. So either use pip install Pytest or uv add Pytest. In the previous file, we tested our calculator with Unittest, and it took a fair bit of boilerplate. Now let's rewrite those exact same tests using Pytest. Tests become plain functions, assertions become plain assert, and setup becomes an explicit fixture you opt into per test. To get started, we will import Pytest. Then we will create the same calculator class. And this class still contains the value property, the add method, the subtract method, the multiply method, the divide method, and the reset method. The only difference in this file will be that we will be using Pytest to test the code. And the very first thing we're going to do here is create a fixture, which replaces the Unittest setup method. This decorator tells Pytest that this function is a fixture, providing reusable setup for tests. The fixture function returns a fresh calculator instance for each test that needs one. As you can see here, we return a brand new calculator, just like setup did in the Unittest version. Below that, we're going to create some basic arithmetic tests, and these will be plain functions. No class is needed. Starting with the test add function. This is a plain function. Again, we don't need any class for this. Pytest discovers it because the name starts with test underscore. And here we'll add 5 and then 3, and we will use a regular assert. Pytest will show a detailed difference if this fails. Then below, we'll test subtract, test multiply, and test divide. And for all of these, we're just asserting that the value is equal to the expected value. And already you can see the difference. There's no class, there's no self, no setup method. Each test is just a function that asks for the fixtures it needs. And instead of using self.assert equal, we write plain assert. Pytest's assertion introspection means when a test fails, you get a detailed breakdown of exactly what went wrong, which is often better than Unittest's output. Below these tests, we will create some more tests, which cover the edge cases. And once again, we will test that dividing by 0 raises an error, and that dividing by 0 gives us the proper error message. For the first one, we use with pytest.raises, followed by the error we're expecting. For the second one, we do the same thing, except this time we use the match argument. And here we specify that the error must match cannot divide by 0. Next, let's talk about parameterized tests. And here's where Pytest really pulls ahead. With Unittest, testing multiple inputs meant writing duplicate test methods or using the awkward subtest context manager. With PyTests at parameterized decorator, you define your test once and provide a table of inputs. PyTest runs it once per row and labels each result clearly. So again, this decorator tells PyTest to run this test once for each set of parameters. Here, we provide the names of the parameters that will vary across test runs. Then here we create a list of tuples, and each tuple in this list represents one test case that PyTest will run independently. For example, here we have the initial value, followed by the operation, followed by the operand, and what's expected. And we will use this decorator on this function, which tests arithmetic operations. And just like we wrote up here, we have the initial value, the operation, the operand, and what's expected. And since this test returns nothing, we will return none. Now the first thing we're going to do inside here is create a calculator with the test case specific starting value. Then we will dispatch the right operation based on the string we received. If it's add, we will add. If it's subtract, we will subtract, and so on. And finally, we will verify that the operation produced the expected result. And just like that, we managed to cover 7 test cases with one function. PyTest runs each row as a separate test with clear labeling in the output. If one case fails, you know exactly which parameters caused it. Next, let's create a parameterized edge case, which means dividing by 0 with different starting values. So once again, we will use the parameterized decorator, provide the parameter that varies across these test cases, and the different starting values. One which is 0, positive, negative, and a float. For the function itself, we will create a new instance of this calculator using the initial value. And then we will verify that a value error is raised when we try to divide by 0. This should always raise, no matter what the starting value was. Next, let's create some state management tests. Starting with a test that tests that a fresh calculator starts at 0. And here we will assert that. Then we want to test that reset puts the value back to 0 when it's called. So here we'll add 100, call reset, and assert that the calculator.value is set to 0. And finally, we want to test the custom initial value. And this will test that a calculator can be created with a non-zero starting value. So here when we provide an initial value of 42, we'll make sure that it actually did that. And finally, let me show you parameterized chained operations. So as always, we will use the parameterized decorator for testing different chains of operations. And these will be the 3 parameters that define each test case. Then we will define a list of tuples. Here we have the initial value, the operations we will perform along the way, and what the final value should be. And we do that 3 more times. Then below, we create the actual function, which contains or uses these parameters. Here, we will create a calculator with the test case's starting value. Then we will loop through each operation in the chain, and depending on which operation was specified, we will perform that operation. And finally, we will verify that the final value matches what we expected. Now to test this, we can open up the terminal and type in pytest, followed by the file name, which right now is main.py, -v. And as you can see, it will go through all of the tests and tell us which ones have passed. But I also want to show you what happens if we have a test which doesn't pass. So let's go up to this section right here, and we can change this line to state that 10 plus 5 equals 14. As soon as we open up the terminal and run pytest, you'll see that one test failed, and it will tell us exactly where it failed. Here we had an initial value of 10, the operation was set to add, the operand was set to 5, and the expected output was 14. So if the logic doesn't add up, whether it's the fault of the function or our own stupidity, pytest will catch that and tell us exactly what went wrong. It will also tell us how many tests passed and how many failed. And that's the full rewrite. To compare them, here's the side-by-side. Unittest uses test case subclass, setup, self.assert equal, and self-assert raises with manual message extraction, while PyTest uses plain functions, opt-in fixtures, plain assert, and PyTest raises with built-in match and parameterize. Or parameterize. I have no idea how to say that. The real payoff comes as your test suite grows. Less boilerplate means less code to maintain, and a test suite that's easier to scan at a glance. But yeah, that just about covers everything I wanted to talk about in today's video. Do let me know in the comment section down below whether you have any questions or suggestions for future videos. But otherwise, with all that being said, as always, thanks for watching, and I'll see you in the next video.